thank you very much first to the organizer, to Sylvie and Guillaume, and to the institutions which sponsor this event. It's a great pleasure for me, of course, and great honor to be to participate in this celebration. So I'm going to talk on Lagrange and sound, some of his earliest works, actually. And first, I would like to show you the title page of the first volume of the Miscellanies here. Oops, sorry. Of a private society founded with a couple of friends, his former students at the School of Artillery in Turin, where he was teaching mathematics. And so this is a title page, and the most, no doubt, the most important memoir in this volume is Lagrange's one of his own contributions, which is a memoir on sound that you see here on the right. And so I read you a piece of the introduction because it's interesting in itself. Quoique la science du calcul ait été portée dans ces derniers temps au plus haut degré de perfection, il ne paraît cependant pas qu'on se soit beaucoup avancé dans l'application de cette science aux phénomènes de la nature. Well, here he's expressing, a pretty common opinion at that time, is that the most advanced mathematical analysis of the time, which was mostly the mechanical fluids of Euler and D'Alembert, had little contact with the experimental world. It really was more theory on paper. So Lagrange wanted to remedy this defect, to fill the gap, so to say. So that's what he's trying to do in this first memoir. But now one may wonder why, as a young budding mathematician, does he pick this topic of sound? Well, it is his first really important published memoir, the one through which he became known, although he had been working, of course, on the calculus of variations earlier. So, we need to understand why he chooses this topic on sound. So a first guess would be to say, well, perhaps because he had a taste for music. Well, here is what he had to say about music. Je l'aime parce qu'elle m'isole, j'en écoute les 3 premières mesures. À la 4e, je ne distingue plus rien. Je me livre à mes réflexions, rien ne m'interrompt, et c'est ainsi que j'ai résolu plus d'un problème difficile. So I don't think this is a plausible explanation. So you have to look somewhere else. So first idea is that, well, there is a traditional connection between mathematics and or arithmetic and music from Pythagoras to Euler. Perhaps more important, there had been recent progress in the 18th century and rather vivid controversies on the physical mathematics of sound, implying the most famous important geometers of the time, Daniel Bernoulli, Jean-Laurent d'Alembert, and Leonhard Euler, who, by the way, the 3 of them had a strong interest in music, unlike Lagrange. So I think in this respect, Lagrange was more, it was more like Newton, who is reported to have fallen asleep during a concert of Handel playing, and yet was the man who produced the first mathematical theory of sound in his Principia Mathematica. So I have to tell you, of course, before addressing the contents of Lagrange's memoirs on sound, there are 2 of them, of these early memoirs, I have to tell you something about what was known about sound in this in the period or before him, what was the main notions that were known, about the physics of sound and the mathematics of sound. Well, the first basic notion for musical sound is a connection between pitch and frequency. So this was more or less uniformly accepted, say, after 1600, and basically everyone agreed that sound, musical sound, a tone, if you prefer, is a periodic succession of pulses. This was the idea people had in mind, and so the frequency be giving the pitch of the sound. Then about harmony, until, say, the early 19th century, the dominant theory of harmony was a theory of coincidence of the pulses of the 2 superposed sounds. Here you have in the diagrams that up there, which is all, does it work? No. You have the case of a fifth, so a ratio of 3/2 for the, and you have the pulses represented, the periodic pulses, and you see frequent coincidences here, here, etc. It's not difficult, but anyway, you see them. And so that was, those frequent coincidences is the feature that was supposed to be pleasant to the ear. Now, what about the propagation of sound? The propagation of sound, well, the modern idea that we have now, sound is about waves of compression. The air is elastic, and then you have those waves of compression without transport of air. This idea became available around 1670 and a little later. It is found in the writings of Pardis, Newton, and Huygens. And and so the most detailed and mathematical version of it is found in the Newton's Principia, where you even have a formula for the velocity of sound, the square root of the pressure time. Well, it doesn't work very well, this, but anyway. You see it, the pressure over density. And the way Newton obtained this is basically by considering a slice of air within a traveling wave, and saying that he applied this is second law, the law of acceleration, to this slice of air, and he shows that in order to have a balance between the product of mass times acceleration and the gradient of pressure, you must have this expression of the velocity, which is written up there. Okay, so this theory of Newton was regarded by even the most learned geometers of the time as very difficult theory, and they tried to simplify it to make it clearer. This is the case of Johann Bernoulli II and also Euler. But there remained the well-known discrepancy that well-known to Newton already between the theoretical value and the measured value of the speed of sound. And you know that this discrepancy was actually not solved by Lagrange, but much later by Laplace and Poisson. It has to do with the fact that the compression of air is adiabatic and not isothermal. So, but this is irrelevant to our story. What is much more relevant is to realize that this idea of sound as a compression wave, which is so obvious to us, was not actually obvious at all in the early 18th century, not only because Newton's reasoning was difficult, but because there was an alternative conception of the propagation of sound, which was quite popular and defended by very important and influential people like Méran, who was for a long time the secrétaire perpétuel de l'Académie des Sciences, for the Abbot Nollet, and in Cambridge, England, the very influential Robert Smith too. All these people believe that sound propagation had to do with the resonance of successive particles of air. So you had to imagine that little resonators all tuned at the same frequency and a resonance going from one particle to the next. And so that means that for every frequency to be propagated in the air, you needed a different class of particles. That sounds a bit complicated, but in fact, those people had good argument against Newton and good for, which I'm not going to detail, for their own theory. Okay. So Lagrange had read quite a bit on the topic on vibrating strings, and he was aware of fairly foundational work, mostly experimental, by Joseph Sauveur at the beginning of the century, where you have developed the idea of complex sounds, starting from the basic experience that was well known, for instance, it's described by Mersenne in the previous century. The fact that when you play a tone, a musical tone, usually if you have a good ear, and if the tone is grave enough, in fact, you can hear a couple of harmonics. You don't hear only the fundamental, you hear also a couple of harmonics. So that suggests some complexity of sounds. And he had the idea to trace this complexity to a complexity of the motion of the string emitting the sound. And he was indeed able to produce not only of course the fundamental here, but also harmonics, like here you have the fifth harmonic. So, and he believed that in general you had a superposition of such motions that produced the effective sound. So here's this idea, and also he has a theory of beats, and which depends on the coincidence theory of harmony, which I mentioned later. And for him, the dissonances we hear when you superpose two sounds of of neighboring frequency have to do to the beats which correspond to the beats for them are just rare coincidences between the pulses of the two superpersons. It's always in terms of pulses and coincidences conception, and that Lagrange is going to adopt, and which is of course adopt, but not at our conception. Now, on the more mathematical side, you have an important memoir by the Taylor of the Taylor series, Brooke Taylor, in 1713. And okay. So in this memoir, you have an application, the first application of Newton's mechanics to the problem of vibration of strings. And so the idea, reasoning is pretty simple. You have first here, you have he calculates the force acting on an element of the string, and he shows that in the first approximation is given by the second derivative of the ordinate here. He, by some kind of hand waving, argues that this force should be proportional to the ordinate, and also he uses, it's not very clear, but it's the second derivative of y here, because all my, unfortunately, the policies are not the same as the original. So this is Newton's law of acceleration here. So if you integrate this differential equation, you get this double sign mode. So that's the only mode, that solution that Taylor was aware of. No, this one. Okay, so this is only a starting point, because you have a much more general, sophisticated theory of small vibrations in general by the Bernoullis, and especially Daniel Bernoulli in the sequence of memoirs. So Bernoulli develops a general notion of simple modes of vibrations that are sine modes, and given by sine functions of time. He has the general expression of the superposition principle, and the idea that an arbitrary vibration can be obtained by simply superposing simple modes of vibration. And interestingly also, he has this notion that so this harmonic, that's what we would call now harmonic analysis of this vibrational phenomenon, has real physical meaning. For him, the harmonic components of a sound or of a vibration of a string, they exist really separately. They exist physically because he was able to hear them, those harmonics. And so he believed that if you had a sharp eye enough, you would be able to see some substructure in the motion of the string that would express those harmonics. Well, the next step now is D'Alembert's theory of vibrating strings in 1746, which is really a landmark in the history of science, since you have here first partial differential equation of physics, and with the sigma is the mass per unit length, T is the tension of the string here, and through a very ingenious method, he was able to find the general integral of this equation here as a sum of the function of ct plus x and ct minus x. And there followed, because Euler gave a similar derivation later, but they deeply disagreed, and that was a long disagreement that lasted until D'Alembert's death, basically, and a very bitter at times disagreement, about the degree of generality of those functions f and g. According to D'Alembert, the whole calculation, the whole reasoning made sense only for what was then called at that time continuous function or regular function, which were functions given by, say, a single formula, algebraic formula. And this is close, but not quite to our modern concept of analyticity. So Euler instead said, well, no, this solution, it works actually for any kind of irregular shape of the string. If it is a string at the beginning, you can very well tolerate irregular functions there. So now, there is at least one point on which they agreed, D'Alembert and Euler. They agreed against Bernoulli, that you couldn't produce this general solution here by superposing Bernoulli simple modes of oscillation. This is this kind of harmonic analysis. They believe it was not possible to generate the most general vibration in this manner. They had various arguments about that, which of course retrospectively are all wrong. But in the current state of analysis and the foundations of analysis, it was really not possible to have any kind of definite argument in all those polemics. And of course, all these polemics are important in the history of the concept of functions, in mathematics and in the evolution of harmonic analysis. I'm not going to give more details, but you will see how Lagrange handles these problems. Now I should mention, lastly, that Sauveur, Euler, and Bernoulli also dealt with flutes, and simply by analogy with musical strings, you just have to imagine that a column of air is made of slices of air that behave like the element, basically, formally, as the elements of a string, an elastic string. Although it would be more for longitudinal vibration instead of transverse vibrations, but the equations are the same in the first approximation, of course. Okay, here we are. Now we're ready to see what's the contents of this Lagrange memoir on sound, this first memoir. So here is the outline. First, you have in this memoir an attack against Newton's theory of sound. And it's always good, for a budding mathematician like Lagrange to be able to prove a genius wrong. So he starts with that. And then he has his own theory of vibrating strings. And he has a theory of propagation of pulses and, on a string or in air. And finally, he has acoustic problems. He deals with more concrete physical acoustic problems. I will be very brief on his objections to Newton. But his idea is that when Newton did his reasoning, actually, he was not considering any type of wave. Newton was reasoning on a sine wave. And but Lagrange realized that the reasoning worked just as well. Newton's reasoning seemed to work just as well if you took different shape for the wave. And he believed that was absurd. How could possibly a wave propagate of any shape, propagate without change of shape? At that time, he believed that was an absurdity. Well, unfortunately, he published this, and he realized it was wrong only after publishing the first memoir. So he became aware that his own theory actually made exactly these predictions, that any shape could be propagated without change of shape. And in the approximation he was dealing with. So he corrected this in the second memoir, and I'm not going to come back to this. And of course, he had to modify his objections against Newton. That didn't work anymore. But now I come to the core of Lagrange's memoir, which is really the solution, his own solution of the problem of vibrating strings. Well, his strategy is first to discretize. So there is a corresponding discrete problem. Well, this idea of discretization was, of course, not new. It had been abundantly used by Bernoulli and Euler. And actually, all those calculations of Lagrange, they had been a good part anticipated by Euler, but Lagrange didn't know that. So the problem is what physicists today call a linear chain of oscillators that you have like above here. And then you have a system of equations, which are the discrete version of the equations of vibrating strings. So, and you have boundary conditions. I will take boundary conditions for which the string is always originally at rest, to have simpler formulas. So he basically, the technique for resolving this system is what we would now identify. It's borrowed from D'Alembert, in fact, kind of strategy, and it's a strategy of diagonalization in modern terms of the matrix, which is in the right-hand side of the system of equation. So after doing that and fairly complicated calculations, I must say, for several pages, he gets here this formula here with sine functions, sine modes, Bernoulli modes that are occurring there. And okay, but this is only a first step. Second step, it takes the limit of the continuous limit, where you take the number of oscillators or masses of loads of the string are going to infinity. And then you get something like that, which is, now you would seen that the Fourier series development in terms of side function with the expression of the coefficients in form of integrals. And he gets this, but to him this is only an intermediate steps. What he does next is to use the trigonometric formula, and thanks to it he arrives at this final formula for the solution of the problem, which is in fact the formula which is given by the Euler-D'Alembert method. This y bar function here, it is this function here, it is the odd periodic of period 2L function, which is an extension of the original shape of the string. So here I took, for the original shape, I took a plucked string here of length L, and so this is this function y bar. So this is the solution with the proper boundary conditions that you have. Okay, so now Lagrange's point here is that this whole calculation, in his opinion, it works since you start from a discrete problem. You can, by a limit of a discretely loaded string, you can obtain any irregular shape you wish. So it says, he gives reason to Euler in this debate between Euler and D'Alembert, saying you can take this type of solution is valid for any irregular shape you can imagine. So here is his conclusion of this part of the memoir. Voilà donc la théorie de ce grand géomètre mise hors de toute atteinte et établie sur ce grand géomètre, c'est Euler, hein, mise hors de toute atteinte et établie sur des principes directs et lumineux. Vous voyez qu'il n'est pas si modeste, hein, qui ne tiennent en aucune façon à la loi de continuité que demande M. D'Alembert. Voilà encore comment il peut se faire. And here, so this first part of the quotation, so it's clearly siding Euler against D'Alembert in this debate. And the second part is in fact a rejection of the Bernoulli simple mode analysis, or harmonic analysis, in the infinite case. Here's what he says. Voilà encore comment il peut se faire que la même formule qui a servi pour appuyer et démontrer la théorie de M. Bernoulli sur le mélange des vibrations isochrones, lorsque le nombre des corps immobiles était fini, nous en dévoile l'insuffisance dans le cas où le nombre de ces corps devient infini. En effet, le changement que subit la formule en passant d'un cas dans l'autre est tel que les mouvements simples qui composaient les mouvements absolus de tout le système s'anéantissent pour la plupart. Et plus loin, il dit il est vraiment fâcheux qu'une théorie aussi ingénieuse, celle de M. Bernoulli, et qui aurait pu sans doute jeter de grandes lumières sur des matières également obscures qu'importantes, se trouve démentie dans le cas principal qui est celui auquel se rapportent tous les petits mouvements réciproques qui ont lieu dans la nature. So, it might sound a little mysterious to him what he's meaning there, because, well, or if I go back, to his calculation, from a formal point of view, it seems pretty clear that he does have something like a formula, what we know, we could see there, a formula for Fourier analysis in the continuous case. And then, but he tells you that it makes no sense. So what does he really mean there? Well, I think what he means is that basically, take for instance the case of a plucked string. So with the original shape of the string will be a triangle. You do a harmonic analysis of this triangle. If you take the first harmonic here, the fundamental, you have this black curve here. You take the third harmonic, which is the next one, in green. You take the superposition, you get this blue curve. So you see that this blue curve in some way is still reminiscent of the modulation of the third harmonic. But if you go higher and higher in harmonics, you don't see this modulation. And so that's what he means, that in the limit of sufficient perfectly efficient amount of harmonics. So all the fine structure that should reflect the presence of harmonics is lost. That's what he means. So, but you will see that he will tell us something a little different later. Now I come to the acoustic part of more specifically physics, in the memoir. So he does spend a bit of time justifying the observations of Sauver and those multiple modes, etc. But and discussing the phenomena of beats, etc. But this is rather straightforward. So I'm not going to detail this. And he has a rather rough theory of flute, so rough that he even assumes that he has notes of oscillation at the two extremities of the flute, if of course not true in the opening of the flute. He has a discussion of propagation of sound in air, but only for pulses. And here, anachronistically, I use the Dirac delta function, but in substance, it's really what he's describing, because he starts from the discrete problem where you have one of the discrete loads, which is pulled from its position of rest, and all the other still original position. All the other are undisturbed. So you have kind of something that looks like a delta function, if you want, for a dense. And it shows that what happens in this case is that your original pulse is going to split in two, in the two directions of the opposite directions of the air column of the string. And so you have, with opposite velocities, you have a propagation of pulses in the two directions from the original pulse. Then he has, in the same line, always with pulses, but he has a discussion of echoes. He has a discussion of, the principle of superposition is there, of course, deduced from the linearity of the equation. He has an interesting discussion of what was called at that time, or a little later actually, Tartini's third sound. So this kind of perhaps will seem exotic to you, but this the Tartini here is Giuseppe Tartini, the famous Italian composer who wrote the sonata, the famous sonata of the Devil's Trills. And Tartini had also authored a couple of years earlier an important treatise of harmony, of a theory of music and harmony, which was based in a good part on this notion of third sound. So what is the third sound? Well, if that he was actually, Tartini believed wrongly that he was the first to observe that. In fact, it was known before. But if you take a tone and you play at the same time the exact upper fifth of this tone, okay? And if you play loud enough, you will hear not only those two tones, but you will also hear the octave below the lower tone. And so for Lagrange, the explanation was obvious. Well, the frequency of this lower octave, it's exactly the difference of the frequencies of the two superposed tones. So this has to do with this is solved by the coincidence theory. It's just the frequency of the coincidences of the pulses. So that's his reasoning, which unfortunately was quite popular until basically Helmholtz's work on combination tones. That's what we now call combination tones in modern acoustics, and it has to do with nonlinearity, in the perception of sound in the air. That's why you have to play your two tones strongly if you want to hear those combination tones. Okay, so this is only one part, of or the whole discussion about harmonies that you have and the theory of harmony that you have in Lagrange's memoir, which is fairly extensive. And there, the two main theories he has to compare, with Tartini was new and not so important yet, but he was comparing Euler's theory of the tentamen of 39 and Rameau's theory. So Euler's theory was a more arithmetic theory, based on the simplicity of ratios representing the superposed sounds. And Rameau's theory instead, Rameau claimed to base it on physical facts. And one basic fact was this complexity of sounds that I told you about earlier, the fact that when you play a musical tone, you also hear a couple of harmonics. And he took this, as really a guide of nature toward, nature gave us toward harmony. Well, but there, Lagrange followed Euler. He believes that it was more about arithmetic. And in particular, he denied, actually even went to deny the existence of harmonics in the case of a plucked string, which may seem bizarre to you. And his idea is that if you heard, because he did hear harmonics in this case, he heard them, he said, well, this is not because of the string, it's because the string, in a string instrument, there always is some sounding board, or there's something around it, other objects, and those harmonics are produced by the resonant objects around. And he proposed a crucial experiment to say, well, if we experimented with a very isolated vibrating string, we should hear only the fundamental and not the harmonics. Unfortunately, he didn't do the experiment. It was done toward the end of the century by Euler, and Euler, of course, found the result against Lagrange. But in any case, that's remained controversial for a long time. This idea, because his intuition is that in the case of a plucked string, the motion is fairly simple. And so how could there be a substructure of harmonics, audible substructure of harmonics for such a simple triangular shape? So he couldn't really understand it. This has to do with his objections to Bernoullian harmonic analysis, as I told you before. Also, I should mention that, of course, he realized, like as other people did before, that all the existing theories of harmony at that time had defects, and they were making some wrong predictions, that there were some intervals that were pleasant to the ear, consonant if you prefer, and yet predicted to be dissonant by available theories. So his conclusion is that harmony was, in a good part, probably also a question of taste and habits, and not only a question of arithmetic or physics. So now I come to the reception of this first memoir on sound. Well, there is one person who was probably pleased. It's the Duc de Savoie, whom you see here in a gracious company. And if you have very sharp eyes, you could see that the little angel here is offering a copy of the Miscellanea Torinensia. It's written here, it's a date too. And why my deduction is come from the fact that he was pleased is because, as I told you, this volume was a volume of a private society. Lagrange named it a private society, and it became the Société Royale de Turin in the second volume of this series. So it must have been approved by the king, obviously. Unfortunately, our Turing expert is not here today, so. I wanted to know more about this story, but okay. Now I come to the more scientific reception. Euler, as you can imagine, was thrilled. Ayant reçu l'excellent présent que vous avez eu à la bonté de m'envoyer, je l'ai d'abord parcouru avec la plus grande avidité, et je n'ai pu assez admirer votre adresse dont vous maniez les plus difficiles équations pour déterminer le mouvement des cordes et la propagation du son. Je vous suis infiniment obligé d'avoir mis ma solution à l'abri de toute chicane. Les chicanes, c'est d'Alembert, bien sûr. Et c'est après vos profonds calculs que tout le monde doit à présent reconnaître l'usage des fonctions irrégulières et discontinues dans la solution de ce genre de problème. D'Alembert, on his side, actually was also, despite the fact, that in a way Euler had, very politely and flattering D'Alembert in other parts of the memoir, but he had taken side with Euler on this problem in a way. But D'Alembert was quite able to recognize already, the power of Lagrange's mathematics. And here is what he writes. Votre dissertation sur le son est pleine des recherches les plus savantes et les plus ingénieuses. J'ai surtout été enchanté de la manière dont vous parvenez à une formule générale pour trouver le mouvement d'une corde chargée d'un nombre infini de poids. That's a discrete problem. But then starts more criticism. Cependant, je ne sais si vous n'auriez pu trouver une méthode plus simple. J'ai peine à croire que cette solution exige nécessairement un si grand appareil de calcul. je penserai au premier moment de loisir que j'aurai, et s'il me vient quelques idées sur ce sujet, j'aurai l'honneur de vous en faire part. Well, he was right actually that the calculation of Lagrange was not as simple as possible. The reason is that today the way we do this calculation is by exploiting the orthogonality of the simple modes. But he was not aware of this. And he became aware of it in the second memoir, although it's done in the continuous case, not in discrete case, but obviously he found a much simpler way to do. Okay. He found a much simpler way to do this type of calculation. Okay, but the most serious criticism is the last one. À l'égard de la méthode par laquelle vous passez du nombre indéfini des corps vibrants au nombre infini, elle ne me paraît pas aussi démonstrative qu'à vous, mais il serait trop long de vous dire mes difficultés sur ce sujet. Well, he actually will give his criticism, but in public, in the first volume of his opuscule, and Lagrange will immediately respond in a polite, respectuous way, and even, in fact, accepting a part of Lagrange's criticism, to the point that he will completely omit the discretization in the second approach of the second memoir. Indeed, even from of course, from our point of view, the way Lagrange takes this continuous limit is very sloppy, but it was sloppy even in contemporary standards. It was sloppy to D'Alembert, at least. So what does he do in his second memoir, which is published in 61, actually, but written in 60? Well, first he comes back to this attack of Newton, which he realizes now must be wrong, but he realizes now that for the, not for stationary waves, but for propagated waves in one direction, you can have propagation of any pulses of any shape f here without change of shape, just translation of it. Then he gives a new solution for vibrating strings, which I'm going to detail. He writes the equation of propagation in 3 dimensions now. Before it was all in 1 dimension. He treats the case of spherical waves and also the propagation in a cone. He treats, or a cylinder, but a cone in general also. He gets beyond the linear approximation in fairly complicated calculations. Actually, his purpose is he was trying to see whether, if you take into account the nonlinear terms, in the Euler equations for the fluid motion, if by any chance you wouldn't be able to solve the discrepancy between the experimental and the theoretical formula for the speed of sound. The result was negative. He did, he calculated the first corrections, he realized that he didn't solve anything. The correction was way too small to explain the discrepancy, which is pretty big. It's about 15%, in normal conditions. So then he gives a very good, although still simple, but a theory of wind instruments and based, on the general equations, or his general equations of solutions for propagation in stationary waves. He corrects, his earlier misconceptions there too. And the most complicated case he treats is the case of trumpets that are not conic, but that have more a shape with a broader opening, broadening here, like in this the case of these angels, these all style trumpets. And he was perfectly aware of the fact that in general, if you take air oscillating in a cavity of arbitrary shapes, we all know that the proper modes of vibrations have incommensurable frequencies in general. This is actually the principle of the Helmholtz resonator, which is spherical. So if you want to have a pleasant sound in commensurable frequencies, like for a trumpet, you have to shape the trumpet in a proper wave. And so he tried to find the mathematical condition for the shape that gives you a harmonious sound. So that's what he did, and but what is interesting is that led him to some mathematical problem, which in fact permitted him to give a general concept of a harmonic analysis toward the end of the memoir. which is something I think quite important, but not many people seem to have noticed. So first, how does he now do, what is his new solution of the problem of vibrating strings? Well, basically, the strategy is the same as a discrete problem. I told you there was a certain matrix that he was diagonalizing, but now, instead of the matrix, he directly diagonalizes the differential operator here, d square over d square, and so introduces this eigenfunctions that we would say today here, MR, which will be sine functions, of course, and he calculates those what we would now call the Fourier coefficients of the function y here by those integrals. So those here it should be a second time derivative here of AR. So for the ARs are just behave like so follow the equation of simple oscillations, and so you integrate this again. You use some trigonometry. And you arrive at this expression of these coefficients here in terms of this function y bar here, this odd periodic extension of period 2L of the original shape of the string, I remind you. So now if you compare those two expressions here, and here of the Fourier coefficients, you see that they involve different. Here you have this expression. He believes that if all the Fourier coefficients is equal without any demonstration, he says, well, the functions from which they are built must be equal. So you must have this relation here. And so he has arrived at the same solution as in the previous memoir to the problem of vibrating strings. And again, he believes this solution doesn't require the function y to be a continuous or regular function, say. And why he believes that? Because he tells you, well, it doesn't matter. Sure, you have a differentiation to perform, on this when you write the equation of motion. But in reality, this differentiation can be absorbed when you construct those AR coefficients by integrations by part, and it will bear on the MR functions which are regular. So that eliminates any difficulty in his opinion, and it's kind of similar to the strategy of modern distribution theory in a way. You solve all the problems by shifting the derivation on some kind of regular function by integration by parts. Very clever. Not very convincing for contemporaries. Now, in this reasoning before, as you see that Lagrange doesn't need to know how to express the function y in terms of its Fourier coefficient, to speak anachronistically. He doesn't need to solve this problem, but he will solve it anyway in the context of the problem of trumpets, as I mentioned earlier, just at the very end of his memoir, in fact. So what does he do there? Well, he tells you, he thinks that in general, this function y should be expressible in terms of superposition of certain functions PR with the coefficients AR. And I think he doesn't actually justify this, but I think it was obvious to him has a counterpart, because this is true in the discrete case, so you just transpose what is true in this case. This is a problem of completeness here, but he has never ever proof in terms of completeness of the base function in the case of Lagrange. He just has an intuition of this completeness. So what he does then is injecting this expression into the expression of the Fourier coefficients, and he gets this orthogonality condition you must have between the M and the P's. And then he shows that if you take the P's satisfying the same differential conditions equation as the M's, the earlier M's and the proper boundary conditions, you can exploit these identities here to show that the orthogonality here. So you have two different values of R and R, so this is different of 0, and this must be 0 by double partial integration. So structurally, what we recognize here is exploiting, the self-adjoint character of the differential operator. And you would think I'm doing something completely anachronistic reading, but not so much, because he's quite aware of those. The fact he's reasoning in this way, in writing this sort of identity, he sees very well the implied structure there, to the point he will actually consider other differential operators, not just these more complicated ones, that share this property of self-adjointness from or Hermitian character, if you want to speak monotone. En français, on dirait hermitique. Bon. Then, as you suspect, in the end result of this is, the typical Fourier analysis formula, because the P's and M's are all sine functions, so you have just a development into sine function with the expression, the Fourier expression of the Fourier coefficients calculated by integrals. So now here is the conclusion, the scholium. Il est clair que la méthode de la remarque précédente peut aussi être employée dans une infinité d'autres équations de même espèce. That's the kind of generalities I was telling you. Et qu'elle s'applique également soit que le nombre des corps mobiles soit infini ou qu'il soit fini. De sorte qu'on peut la regarder comme une simplification, une généralisation de celle dont nous sommes servis dans le chapitre, etc. Au reste, cette méthode sert à démontrer la belle proposition de M. Bernoulli que lorsqu'un système quelconque de corps fait des oscillations infiniment petites, le mouvement de chaque corps peut être considéré comme composé de plusieurs mouvements partiels et synchrone à chacun à celui d'un pendule simple. So you see that he seems to have changed his mind. Now he's really on Bernoulli's side. He seems to agree that even in the continuous case, you can do harmonic analysis. It also works. So you see, it's a bit bizarre. How can he be contradicting himself so much? I think you find a clue to this seeming contradiction in later writings, where it becomes clear that Lagrange distinguishes between a formal validity of harmonic analysis. You have, this Fourier formula that he has, but he doesn't believe in any physical import of this decomposition. It's purely formal and mathematical, because it still thinks that from a physical point of view, the harmonics in an infinite superposition, they disappear. All the modulations mutually cancel each other. You don't see this substructure. It has no physical existence for him. And indeed, in his subsequent work, he will do very little use, in fact, or no use at all of harmonic analysis. Now, what about the reception of this second memoir on sound? Euler is dazzled, ébloui de l'abondance et de la profondeur de vos recherches. He even writes in 1762, la plus sublime recherche que les géomètres aient entreprise de nos jours avec succès et sans contredit à tous égards celle de la propagation du son. Here, well, this is also self-serving, because in fact he has published about the same time very important memoirs himself on sound. He's quite aware of them. And so it's not only Lagrange who is congratulated there. Euler's, as you know, of course, Euler then went to Berlin to St. Petersburg, and he was replaced by Lagrange in 1766 when Euler went back to St. Petersburg. And of course, considering the tightness of the connection with Euler, this is no surprise. As the relation with D'Alembert were actually also excellent. He had a very lasting, long, friendly correspondence with him. They actually met in Paris, and D'Alembert even supported or tried to support Lagrange, the young Lagrange, financially, intervening, indirectly, so that the king would give him additional financial support. But I think this friendship, of course, he knew how to cultivate it. Certainly, Lagrange was a very diplomatic man, and he was able to flatter D'Alembert properly, and always avoided any any frontal, aggression. Or he always formulated his objection, if he had any, in a very subdued tone. And I think in many cases he simply omitted to say that he disagreed. And yeah, here is typical. Here is a letter that he wrote in 769. Vos remarques sur la théorie des cordes vibrantes de M. Bernoulli me paraissent décisives. I don't think he did, but he writes it anyway to please d'Alembert. And j'admire la constance avec laquelle vous êtes capable de poursuivre le même objet pendant un si longtemps. Pour moi, j'ai ce malheur qu'à force de remanier la même matière, j'en prends à la fin un si furieux dégoût qu'il m'est comme impossible d'y revenir encore, et c'est précisément ce qui m'est arrivé à l'égard des cordes vibrantes. Voilà pourquoi j'ai toujours négligé de répondre à M. Daniel Bernoulli, quoique je puisse le faire avec avantage. Well, I think there he's quite sincere. He was really disgusted with the problem. He didn't like, this everlasting disagreement. He probably had the intuition that anyway, with the foundations of analysis as they were, or as they were lacking in his time, that there was no clear-cut arguments in favor of a position or another. And so he simply gave up, and he indeed stopped writing on those issues for a number of years. And, or in fact, even for the rest of his life, I should say. Okay, so now you know another big step, of course, in his life. He moved to Paris from Berlin, when Friedrich der Zweite, Frederick the Great, died, and D'Alembert was dead by that time, so D'Alembert couldn't help, certainly. But of course, Lagrange, was at the peak of his fame at that time. He was very desired everywhere. The Italians wanted him, everybody wanted him. More on the reception. So now, what about Daniel Bernoulli? Well, those two men, actually, they never met. But there was a mistake on Lagrange's part. Actually, when he visited D'Alembert in Paris, on the way back, he had to travel for Switzerland, and he asked D'Alembert who should see D'Alembert. Oh, don't go see Daniel Bernoulli, probably told him, boring man, and go see Voltaire. And so he went to see Voltaire, who entertained him with anti-clerical stories, and Lagrange was very happy about that. But he didn't see Bernoulli, and in case Bernoulli didn't adopt very friendly, but Bernoulli in his old age was a pretty sour man, and he didn't appreciate much of the new analysis, especially the all partial differential equation-based analysis. So in 762, he published a significant memoir on organ pipes, giving a more intuitive theory based on this notion of simple modes with no partial differential equations. And in fact, we know that he had his theory for a long time, but he published only the bulk of it only so late, probably because now he knew, of course, he was aware of Lagrange's memoir, so he'd have to publish my work now. Well, Lagrange was not too pleased. Here is what he wrote to D'Alembert. J'ai lu le mémoire de M. Daniel Bernoulli sur la théorie des tuyaux d'orgue. Il n'a fait que délayer dans un long verbiage ce que j'avais mis dans quelques formules algébriques dans mes deux mémoires sur le son. Encore ne l'a-t-il fait qu'imparfaitement et dans le seul cas particulier de l'isochronisme et des vibrations. Cependant, il a le front de dire qu'il n'a trouvé dans aucun traité des vibrations de l'air, les vibrations de l'air exactement décrites. Mais je lui donnerai bien sur les doigts. This is about as violent as Lagrange can be, but in a way he was right to be angry, because what happened is that during the next 50 years, whenever you found any kind of exposition of account of the theories of organ pipes or flutes or whatever, wind instruments in acoustic or in a physics treatise, the theory which is referred to is always Bernoulli's theory and not Lagrange's. Lagrange's, with all these partial differential equations, was too sophisticated, and most people couldn't get it. Okay, now what about Fourier? Well, I showed you that if you look carefully in those memoirs, you see more than anticipations, actually, of Fourier analysis, of harmonic analysis, although not so well founded, but you have quite a bit of it in this Lagrange memoir. So, of course, the question is, was Fourier inspired by Lagrange? Well, we know, of course, he knew Lagrange. He attended his course at new École Normale de l'an 3. And here is actually how he wrote home about Lagrange's lectures. He writes, Lagrange, le premier des savants d'Europe, paraît avoir de 50 à 60 ans. In fact, he was 59 at that time. Il est cependant plus jeune. Bon. Il a dans les traits de la dignité et de la finesse dans la physionomie. Il paraît un peu grêlé et pâle. Sa voix est très faible à moins qu'il ne s'échauffe. Il a l'accent italien très marqué. Il prononce les S comme des Z. Il est très modestement vêtu en noir ou en brun. Il parle familièrement et avec quelque peine. Il a dans la parole l'embarras et la simplicité d'un enfant. Tout le monde voit bien que c'est un homme extraordinaire, mais il faut l'avoir vu pour reconnaître un grand homme. So this funny description, according to our testimony, seems to be actually pretty accurate. It gives a good feeling, I think, of the man Lagrange as he was. And so now, what's happened, when Lagrange became aware of Fourier's memoir on heat propagation? There is a myth that Lagrange rejected it, and I think he actually did. He had some details, criticism of detail regarding some points of rigor, and but I think probably he simply, which was not too pleasing to him, he recognized something that he had largely anticipated himself. And in my opinion, it is the probable reason why, bizarrely, in the second edition of the Mécanique analytique, Lagrange introduced, at the end of the book, he reproduced his old theory of 59 of arbitrary strings. I think just to tell, okay, look, I did that in a number of years ago, and here you have something which is not so different from Fourier analysis. Of course, he was probably aware, and we should certainly be aware of the fact that Fourier's conception of harmonic analysis is much broader and much more physical and less formal than Lagrange's. And certainly one of the essential points for Fourier's approach is that he was able to see, the importance, the usefulness of this sort of analysis in solving physical problems. And instead, Fourier was rather pessimistic for uses of this sort of analysis in physics. So now I think I need to conclude. It's largely time. Yeah. And I think it is clear to me, that these memoirs contain, of course, from a there are two sides. There's a more mathematical side and a more physical side. On the physical side, you could say, well, it was clever, but it was conditioned, of course, by the context of understanding of acoustic at the time, and unfortunately, rather conservatively in this context, he followed the whole conception of the coincidences, or the coincidence theory of harmony, which proved to be essentially wrong, later. But it was an influential part of his work, and at least his theory of organ pipes was actually close to what or flutes we would now teach. In fact, we would teach now Lagrange's conception, because we have a different conception of what is difficult in mathematics today, and we wouldn't teach Bernoulli, which I feel there are some intuitions of Bernoulli which seems quite bizarre from a modern point of view, and we would feel much closer to Lagrange today. So he's more modern in this respect. Now, on the mathematical side, of course, it's highly impressive. Of course, the two greatest geometers of the time were highly impressed, D'Alembert and Euler. But I think we should also be impressed, at least if you know what was not known or not known at that time, is that by this sort of algebraic structural intuitions, he is able to create new mathematical tools, new strategies of demonstration, to develop, really, he has this strong intuition of very general harmonic analysis, and this is all, I think, extremely impressive. But I will conclude here, and I thank you for your attention.